Hi, myself Dr. S.K. Bush, former HOD, Department of Physics, Cotton University. This is a video lecture in physics for class 12 students. Lesson 2 of chapter 3, Resistance and Resistivity. In this lesson, we'll discuss Ohm's law, resistance and resistivity, the macroscopic version of the equation V equal to IR, and finally, drift of free electrons and the origin of resistivity. Let's begin. Ohm's law. This is a photograph of George Simon Ohm, the German physicist and mathematician. The statement of Ohm's law. The current through a conducting device is directly proportional to the potential difference applied to the device. The above statement does not hold good in all situations. Still, for historical reasons, it is accorded the status of a physical law. A device is called ohmic if it obeys Ohm's law, irrespective of the magnitude and polarity of the applied voltage. Devices that do not obey Ohm's law are called non-ohmic. Let us consider an ohmic device. Suppose a potential difference V establishes a current I in the device. The figure is the graph of current versus voltage in the device, which is in fact a 1000 ohm resistor. The linear nature of the graph tells us that the device is ohmic. Let us now consider a non-ohmic device. The figure shows the graph of current versus voltage in the device. Device is in fact a PN junction diode. We'll revisit the PN junction diode in a subsequent lesson. The non-linear graph tells us that the device is non-ohmic. Resistance. Let a current I flow through a conductor when a potential difference V is applied across its two ends. Then Ohm's law gives I proportional to V, this is equation 1, or I equal to V by R, call it equation 2, or V equal to IR, we call it equation 3. The constant of proportionality R is called the resistance of the conductor. The name resistance is truly appropriate. Equation 2 tells us that for a given potential difference across a particular conductor, the current is small when the resistance is large, and vice versa. The SI unit of resistance is volt per ampere or ohm. Its symbol is Greek letter capital omega. A conductor which provides a specified resistance in a circuit is called a resistor. A resistor is indicated by the symbol as shown. The resistance of a conductor depends on its geometry as well as on its material. Resistance depends on the dimensions of the resistor. Let us consider two identical brick-shaped ohmic conductors of length L and cross-sectional area A. The slabs are placed in contact lengthwise as shown in the figure, and a current I is sent through them. The same current will flow in both the slabs as the slabs constitute a single pathway for the current. If R is the resistance of each slab, then the potential drop across each of them is V equal to IR. This is equation 1. Therefore, potential drop across the two ends of the combination is V plus V equal to twice V. Therefore, the resistance of the combination is R dash equal to 2V divided by I equal to 2 into V by I equal to twice R. Thus, an increase in the length of the conductor by 2 times led to an increase of its resistance by 2 times. Therefore, we may state that R is proportional to length L of the conductor. This is equation 2. Next, we slice the slab lengthwise into 2 equal parts of cross-sectional area A by 2 each, with their length remaining unchanged. Then they are placed one on top of the other as shown. As a conductor, the combination is equivalent to the original slab itself. Therefore, if V is the PD, that is potential difference, applied across the two ends of the combination, then the current in it will be I. Consult equation 1. As the half slabs are identical, equal currents will flow through them. Thus, current in each half slab will be I by 2. Therefore, the resistance of the half slab is R dash equal to V divided by I by 2 equal to 2 multiplied by V by I equal to 2R. Thus, a decrease in the cross-sectional area of the conductor by 2 times led to an increase of its resistance by 2 times. Therefore, we may state that the resistance of a conductor is inversely proportional to its area of cross-section. That is, R proportional to 1 by A. This is equation 3. Combining equations 2 and 3, R proportional to L by A. This is equation 4. Here L is the length of the conductor and A is the area of cross-section of the conductor. Or R is equal to a constant rho into L by A. Equation 5. The constant of proportionality, rho, is called the resistivity of the material of the conductor. The resistivity depends only on the nature of the material of the conductor and is independent of its dimensions. The SI unit of resistivity is given by its defining equation 5 as ohm meter. The inverse of resistivity is called the conductivity of the material, sigma. We have rho equal to 1 by sigma, equation 6. The SI unit of conductivity is the reciprocal of ohm meter, that is ohm meter to the power minus 1. Sometimes the unit mho per meter, MHO mho is ohm backward, is also used. The microscopic version of the equation V equal to IR. The quantities in the equation V equal to IR are macroscopic in character and therefore are directly readable on meters. The same equation may be framed in terms of the corresponding macroscopic quantities. The quantities are the electric field E at a point in the resistive material, the current density J at that point, and the resistivity rho of the material. Let us consider a metal wire of length L and area of cross-section A. All other relevant quantities have been illustrated in the figure below. We assume that the electric field and the current density are constant throughout the wire. Then we have V equal to E multiplied by L, I equal to J multiplied by A, and R equal to rho into L by A. Then using the equation V equal to IR, we get E into L equal to J into A multiplied by rho into L by A, or E equal to rho into J, or J equal to E by rho equal to sigma E, where sigma equal to 1 by rho is the conductivity of the material. Writing in vector form, we get J equal to sigma E. Here, current density J and the electric field E are both vectors pointing in the same direction. This equation is the macroscopic version of the macroscopic equation V equal to IR. Now come to the drift of electrons and the origin of resistivity. Why do certain materials obey Ohm's law? To answer the question, we must analyze the conduction process itself in the material at the atomic level. We will limit ourselves to metallic conductors only. We have already discussed about the free electrons of metals and how they move about randomly within a sample. Let us recall that the number density of the free electrons in a sample of metal is colossally large. For example, 1 cc of sodium contains about 10 to the power 23 free electrons. These free electrons randomly move about in the lattice with speeds as high as 10 to the power 6 meter per second. The randomly moving free electrons suffer frequent collisions with the ion cores in the lattice and also with one another. Given the situation, the collision frequency is very high, of the order of about 10 to the power 13 collisions per second. A free electron loses the memory of its past motion in a collision and then nonchalantly renews its random motion once again. See the adjoining figure, in which 6 consecutive collisions suffered by a free electron have been illustrated. The average velocity of the random motion can be expressed as Vi average equal to 1 by n sum over 1 to n Vi. Here, Vi is the velocity of the ith free electron, and n is the total number of free electrons in the specimen, while Vi bar denotes the average. Clearly, Vi bar equal to 0 as sum over 1 to n Vi is 0, since Vi's are random. That is, Vi's are in all possible directions. For every electrons moving in one direction with a certain velocity, there will be another electron moving in exactly the opposite direction with the same magnitude of velocity. So sum over 1 to n Vi is always 0 in the context of the random motion of the free electrons. Let us now switch on an electric field in the sample. The field will impart an acceleration A to all the free electrons. The acceleration is equal to minus E into capital E divided by M. Here, capital E is the electric field, while minus small e and M are the charge and mass of an electron, respectively. The negative sign in the expression tells us that the acceleration takes place in the direction opposite to the electric field. The velocity gained by a free electron, I, in time ti, in the field is therefore Vi equal to ATI equal to minus small e into capital E divided by M into Ti. This is equation 2. The earlier one we named as equation 1. We should be careful with the notation capital Vi and small vi. The former denotes the random velocity, while the latter is the velocity imparted by the applied electric field. Sooner or later, a free electron is bound to suffer a collision at which it loses the velocity it had acquired under the field. The process of gaining velocity under the field and then squandering it in the next collision repeats itself as long as the field is kept on. This is why the velocity gained by a free electron under an electric field never increases indefinitely, but remains confined between limits Vi and 0. After some time, the free electrons settle down at some average velocity. If tau is the average time interval between two successive collisions, the time interval is called the mean free time or the relaxation time, then the average velocity Vi bar acquired by the free electrons will be equal to minus small e into capital E divided by m into 1 by n summation from I to n Ti equal to minus small e into capital E divided by m multiplied by tau equal to V subscript D. This is equation 3. This average velocity is called the drift velocity of the free electrons, since it gives the velocity of their buck motion in a particular direction, that is, opposite to the applied electric field. The magnitude of the drift velocity is rather small, of the order of 10 to the power minus 5 to 10 to the power minus 4 meter per second. Now, combining equation 3 with current density J equal to minus NE V subscript D. From now onwards, we'll call V subscript D as Vd. We get J equal to N E square tau divided by M into E, equation 4. Here J and E are two vectors. Again, comparing equation 4 with J equal to sigma E, we get the conductivity of the material as sigma equal to N square tau by M. This is equation 5. Therefore, the resistivity is rho equal to 1 by sigma equal to M divided by N square tau. This is equation 6. As N and tau are constants for a particular metal, rho is constant for that metal. Here, M and E are constants for all. Thus, equation 6, which establishes that rho is a constant for a given material, and hence it is independent of the magnitude and polarity of the voltage applied across the material, asserts Ohm's law from a fundamental point of view. Visualization of the drift of free electrons. In the figure, the red lines illustrate the journey of a free electron from A to B. The electron suffers 6 collisions en route. Now, an electric field is applied as shown. The path of the electrons gets slightly modified, which are shown as gray lines. The modified path is actually parabolic, as it should be in an electric field. The electron suffers a drift opposite to the electric field and arrives at B' instead of B, thus suffering a drift BB'. Of course, the drift BB' is very small compared to the total distance traveled by the electron randomly during the same interval of time. It is our common experience that we do not require a retarding electric field to halt the drifting free electrons. Current vanishes as soon as the original accelerating field is switched off. This halting job is also carried out by none other than the collisions themselves. A free electron loses whatever drift velocity it had acquired under the applied electric field after suffering a collision. If the electric field no longer exists, then the free electron is left with only the random part of its motion and a current, which is simply the manifestation of the collective drift of the free electrons, disappears spontaneously. Come to the topic, temperature dependence of resistivity. Like many other physical properties, resistivity too depends on the temperature. For metals, the resistivity increases linearly with temperature over a certain range according to the approximate empirical relation rho equal to rho naught within bracket 1 plus alpha again within bracket T minus T naught, both the bracket closed now. Here, T naught is a reference temperature and rho naught is the resistivity at that temperature. Alpha is called the temperature coefficient of resistance, whose value is adjusted to get the best fit to the experimental values. The room temperature T naught equal to 293 Kelvin is usually taken as the reference temperature. The rho naught for copper at T naught equal to 293 Kelvin is 1.69 into 10 to the power minus 8 ohm meter. This is a graph showing resistivity versus temperature for copper. The figure credit Wikimedia Commons. On the other hand, some alloys like nichrome, nickel, chromium, and often iron, and sometimes other elements, manganese, copper, manganese, and nickel, and constantan, copper, and nickel, exhibit very weak dependence on temperature. This makes them very suitable for wire-bound standard resistors. In the other end of the spectrum, there are semiconductors whose resistivity decreases with increasing temperatures. We will revisit this issue in a later lesson. The temperature dependence of resistivity of metals can be explained from a microscopic point of view. The amplitude of the lattice vibration rises with increase in temperature. This in turn raises the frequency of collisions suffered by the free electrons with the ion cores. As a result, the mean-free time, tau, decreases. Now consider the equation expressing the resistivity of the metal. Rho equal to m divided by n square tau. The equation tells us that the smaller the value of the relaxation time tau, which is the case at higher temperatures, the greater the resistivity rho. Mobility of the charge carriers. The mobility of the charge carriers is defined as the magnitude of their drift velocity per unit applied electric field. Mobility is denoted by the letter mu, which is equal to modulus of drift velocity Vd divided by modulus of the electric field E. Substituting for Vd, the drift velocity, we get mu equal to E by m into tau as the final expression. We'll revisit the topic mobility in connection with the conductivity of a semiconductor in a subsequent lesson. I acknowledge the book Fundamentals of Physics, authored by Halliday, Resnick, and Walker, and published by John Wiley and Sons, Inc., for inspiration. This brings us to the end of the lesson 2 of chapter 3. We will discuss electrical cells, combination of resistors, electrical energy and power, etc. in the next lesson. Till then, goodbye and thank you.